My name is Isai Kumar and I am from ECUD section. My topic is impedance matching techniques. Let us see the matching techniques. The operation of an antenna system over a frequency range is not completely dependent upon the frequency response of the antenna element itself, but rather on the frequency characteristics of the transmission line antenna element combination. In practice, the characteristic impedance of the transmission line is usually real, whereas that of the antenna element is complex. Also, the variation of each as a function of frequency is not the same. Thus, the efficient coupling matching network must be designed which attempt to couple match the characteristics of two devices over the designed frequency range. Let us see the types of matching techniques. First one is the stub matching and the quarter wavelength transformer. In quarter wavelength transformer, there are four types: single selection, multiple selections, binomial design, Chebyshev design. Stub matching. Ideal matching at a given frequency can be accomplished by placing a short or open circuited shunt to distance S from the transmission line antenna element connection. Assuming a real characteristic impedance, the length S is controlled so as to make the real part of the antenna element impedance equal to the characteristic impedance. The length L of the shunt line is varied until the susceptance of the stub is equal in magnitude but opposite phase to the line input susceptance at the point of the transmission line shunt element connection. The short-circuited stub is more practical because an equivalent short can be created by a pin connection in a coaxial cable in a waveguide. This preserves the overall length of the stub line for matchings which may require longer length stubs. A single stub with a variable length L cannot always match all antenna load impedances. A double stub arrangement positioned a fixed distance S from the load, with the length of each stub variable and separated by a constant length D, will match a greater range of antenna impedances. However, a triple stub configuration will always match all loads. That is a quarter wavelength transformer. It contains single selection, multiple selections, binomial selections, and Chebyshev design. Let us see the single selection matching technique. Another technique that can be used to match the antenna to the transformer line is to use a lambda by 4 transformer. If the impedance of the antenna is real, the transformer is attached directly to the load. However, if the antenna impedance is complex, the transformer is placed a distance S0 away from the antenna. The distance S0 is chosen so that the input impedance toward the load at S0 is real and designated as Rin. Here the single selection stub matching, single section stub matching diagram is given. Lambda by 4 transformer is used in the uh, single section matching. To provide a match, the transformer characteristic impedance Z1 should be Z1 equal to under root of R into Z0, where Z0 is the characteristic impedance of the input transmission line. The transformer is usually another transmission line with the desired characteristic impedance. Because the characteristic impedances of most of the shelf transmission lines are limited in range and values, the quarter wavelength transformer technique is most suitable when used with microstrip transmission lines. In microstrips, the characteristic impedance can be changed by simply varying the width of the center conductor. Next to the multiple section, matchings that are less sensitive to frequencies variations and that are provide broader bandwidths require multiple lambda by 4 sections. In fact, the number of In fact, the number and characteristic impedance of each section can be designed so that the reflection coefficient follows within the desired frequency bandwidth prescribed variations which are symmetrical about the center frequency. The antenna load impedance will again be assumed to be real. If not, the antenna element must be connected to the transformer at a point that's not along the transmission line where the input impedance is real. Now the total input reflection coefficient gamma in for an n-section quarter wavelength transformer with RL is greater than Z0 can be written approximately as gamma in equal to rho naught plus rho 1 e power minus j2 theta plus rho 2 into e power minus j4 theta plus so on to rho n e power minus j2n theta, that is equal to sigma n equal to 0 to n rho n into e power minus j2n theta, where rho n is zn plus 1 minus zn by zn plus 1 plus zn. Here the n section lambda naught by 4 transformer is given. Multiplication rho n represents the reflection coefficient at the junction of two infinite lines with characteristic impedance Zn and Zn plus 1. F naught represents the designed center frequency, F the operating frequency. If RL is less than Z0, the rho n should be replaced by minus rho n. For a real load impedance, the rho n and the Zn will also be real. Next, we will see the binomial design matching technique. One technique is used to design an n-section lambda by 4 transformer requires the input reflection coefficient of equation have maximally flat passband characteristics. For this method, the junction reflection coefficient are derived using the binomial expansion. Doing this, we can equate to gamma in of f equal to sigma n equal to 0 to n rho n into e power minus j 2 n theta equal to e power minus j n theta into RL minus Z naught by RL plus Z naught into cos power n theta. And that can be written as 2 into 2 power minus n into RL minus Z naught by RL plus Z naught into sigma n equal to 0 to n c n e power minus j 2 n theta. And from this we have the delta f by f naught formula, that is equal to delta f by f naught equal to 2 minus 4 by pi cos inverse of rho m by RL minus Z naught by RL plus Z naught into Z naught power 1 by n or power 1 by n, where rho m is a maximum value of reflection coefficient which can be tolerated within the bandwidth. The usual design procedure is to be specify the load impedance RL and input characteristic impedance Z0, number of sections n, maximum tolerable reflection coefficient rho m, or the fractional bandwidth 3f by f naught. And to find the characteristic impedance of each section, fractional bandwidth or maximum tolerable reflection coefficient rho m. Step by step design. Now, the reflection coefficient can be made to vary within the bandwidth is an oscillatory manner and have equal ripple characteristics. This can be accomplished by making gamma in behave according to the Chebyshev polynomial. For this Chebyshev design, the equation that corresponds to is gamma in of f equal to e power minus j n theta into RL minus z naught by RL plus Z naught into Tn into secant theta m cos theta by Tn secant theta m, where Tn is a Chebyshev polynomial of order n. Then next, the maximum allowable reflection coefficient occurs at the edge of the passband where eta equal to um, and now the rho m equal to RL minus Z naught by RL plus Z naught into 1 by Tn secant theta m. We can write that it is mod of Tn secant m equal to 1 by rho n into R minus Z n by R plus Z0. Now using these equations, we will get the term gamma in. At last, we will get the theta angle. Theta equal to secant inverse of cos hyperbolic into 1 by n cos hyperbolic inverse of 1 by n into R minus Z0 by R plus Z0. Next, the reflection coefficient gamma in will be written as e power minus j n theta over O m T n secant of theta m cos theta for given in replace by its polynomial series expansion and then match terms. The usual procedure for the semester design is the same as that of binomial as outlined previously. For z equal to secant Vm cos v, the first three polynomials reduced to the given of secant theta cos theta equal to secant theta. In general, the multiple sections, either polynomial or Chebyshev, provide greater bandwidth than a single section. As the number of sections increases, the bandwidth also increases. The advantage of the binomial design is that the reflection coefficient values within the bandwidth monotonically decrease from both ends towards the center. Thus, the values are always smaller than an acceptable and designed value. For the Chebyshev design, the reflection coefficient values within the designed bandwidth are equal or similar or smaller than an acceptable and designed value. The number of times the reflection coefficient reaches the maximum ripple value within the bandwidth is determined by the number of sections. In fact, for an even number of sections, the reflection coefficient at the designed center frequency is equal to its maximum allowable value, while for an odd number of sections, it is zero. Next, next for a maximum tolerable reflection coefficient, the n-section Chebyshev transformer provides a larger bandwidth than a corresponding n-section binomial design. Or for a given bandwidth, the maximum tolerable reflection coefficient is smaller for a Chebyshev design. Thank you.